Me too.
Can I have a look at that?
So, next Wednesday, SIS test. I will provide you with a SIS test revision booklet. It'll take 2 lessons worth. We'll get through that, and that should hopefully get you ready for the SIS test. The SIS test is split into 2 topics. The first topic is basic skills of significant figures and percentage uncertainties and scientific notation. And then the second part is a little mini comprehension. Here's a table, plot a graph, calculate a gradient, those essential skills that you need. Okay? Then, in weeks 5 and 6, we are doing circuits, and there will be a practical, a lab prac that we'll do in week 5. You'll submit it in week 6, and then your exams are in week 7 and 8. And I believe physics is, for us, is Tuesday of the first week. So get it done and dusted. So that's the outline that we have. We've got a SIS test and a practical, then the exams, and then in week 9 we do electricity in the home and safety of electricity, and then I believe our test is scheduled for week 10, Monday in class.
Green appliances.
Applications of electricity. So, let's get into very quick revision. The charge is a fundamental quantity in nature, okay? And it has certain rules. It's conserved and it's not destroyed, and we can do work on charges. Just like we can do work on mass, we can put energy. Do you want a booklet?
Yes, please.
Sure. There you go. Can you throw that? Oh, there we go. So our electron has a tiny, tiny charge. Yet we can move a large amount of charge in wires, and it turns out that we're moving a lot of electrons. If we move a coulomb of charge from one point to another, then we're moving 6 million electrons every second past a point in a circuit. So if I could look at a piece of copper wire, if we had a coulomb of charge moving past, I would have counted that many little electrons jumping across the copper atoms. It's a lot. Okay? Let's continue on to our next... and we went on a little bit of a... this didn't screen capture. We had a wonderful conversation that wasn't screen captured. I had to put out last year's lesson, which wasn't as great. Let's just quickly recall, if I had a meter of copper wire, which is, I was going to pick this one up, but I don't want the power to go out. A meter of copper, here we go. A meter of copper wire that was 2 millimeters in diameter. No, 4 millimeters. Okay, so it's a bit chunkier. So maybe it's this chunky boy here. All right. How many electrons do we have? We do a little bit of density, we do a little bit of chemistry, and it turns out we have lots of electrons. Okay? So just remember, there's plenty of room at the bottom, which is what Richard Feynman said. Now, let's go to current. Current is defined as the flow of electric charge through a point per unit time. We're going to write down the following. I equals Q over T. Okay, this is in your data sheet. Oh, that's the loveliest box I have drawn. Yes?
Do I have to memorize that definition?
No, it's in your data sheet. No, probably not. We don't have time now for what is the definition of current. It would be, here's a circuit, calculate the current. All right? And we have the dimensional analysis, coulombs per seconds equals coulomb per second. Okay? Well, we're going to name that an amp. Capital A, named after a dude, ampere. Okay? You can rearrange this equation whichever way you want. One common way is Q equals IT. Okay? This is your rate multiplied by time gives you the number of events. Okay? So if we've got coulombs per second, multiply it by our unit of time, then we'll get our answer out in coulombs. Okay? Again, even Ampere didn't realize when he was making his measurements of current that he was dealing with a lot of electrons passing through a point. Okay? So let's just finish off. 1 amp equals 1 coulomb per second. Okay? Don't ask me why the symbol for current is capital I. I'm not sure because probably capital C would make things confusing. We've got coulombs there. Now, the unit for the current is the ampere, capital A. I don't know. Let's just write it in again. 1 amp equals 1 coulomb per second, which equals that bloody big number of electrons passing through a point every second. This can often lead students to think that our electrons are travelling really fast. If you imagine zooming in on a point in a wire and counting that many electrons per second, a common misconception is that they should be travelling at, kilometres per hour. They should be whizzing, racing through the circuit. And sometimes you see diagrams with the electrons as little bubbles or circles moving through a wire. It's misleading. They're actually travelling really, really slowly. There's something called drift velocity, which I'm going to bring out my purple not in syllabus pen. There's something called the drift velocity. If you watched a single electron, there's a lot of bouncing, and it's not just going to be nice and uniform like, I don't know, people walking into chapel. It's going to be lots of collisions and backwards and repulsions, but over time...
So it is like people walking into chapel.
Over time, there is a general displacement, let's just call it S, of our electron, okay? So yes, over time, the electrons do move forward. But let's just take my friend dimensional analysis and go that 1 amp is 6.24 by 10 to the 8 electrons per second. Hang on, let me use my dimensional analysis pen. Electrons per second. And if I divided by how many electrons we had in a meter of copper, which we learnt last lesson was 2.14 times 10 to the lots of electrons per meter, look what we end up with. We get a unit of meters per second. 2.92 times 10 to the negative 6 meters per second. All right? They're not moving very fast, but there's lots of them. Yeah. So for them, that's how fast an electron might move. So millimeters in a lesson. If I had a DC current in a wire and we said, all right, we're looking at that electron, we'll come back to it in 50 minutes. And after 50 minutes, it's moved a couple of millimeters. They do not travel very fast. Okay?
Where did you get 2.14 times?
That was the number of electrons in a meter of copper. All right, so obviously, yes, the drift velocity will vary depending on
the electron.
What substance it's moving through. Okay, which we just decided to be a meter of copper. So just remember that there's plenty of room at the bottom. Now let's go back to in the syllabus. Now, Mr. Murray has given you a non-SI unit and a metric prefix. So please remember, convert to seconds. Convert to seconds. And milli is 10 to the negative 3. Okay, so current. No, that's not. That's time. Try again. Time, current, charge. Okay. Remember, you need to show your conversion. So don't just write whatever the number is. Show the conversion.
Is it fine if we do it like in the...
5 times 10 to the negative 3. There's my conversion for milli. And then multiplied by 45 by 60. There's my conversion to seconds. We get 13.5 coulombs of charge. Who can remember the equation from Friday's lesson that's not in the data sheet, but you can kind of figure it out for finding n? Spot on. So you could say Q equals n times your fundamental, and as Matthew rightly said, we could take our charge, divide it by our fundamental, and we'll get a friggin' huge number because we're dividing it by a friggin' small number.
Is that a technical term?
Yes. Scientific notation. I often like asking in tests and exams for students to calculate how many charges must flow. Because again, it's that weird equation that's not quite in the data sheet, but it's not that tricky to figure out if you know what your dimensions are doing. Okay? Let us continue on. So in a circuit, this will be used... Yes? What's up? Talk to me.
Do we know the number of electrons, the charge?
Yes, you should know the charge. It's in your data sheet. It's the fundamental charge. It's written there, 1.60 10 to the negative 19. You need to know, especially in year 12, currently they are learning about the flow of charge. Now, what happens is that your electrons are obviously going to be repelled from the negative terminal. They might go through a circuit, and they're also attracted at the same time. What the battery does is it provides an electromotive force. Sam and Brady, are we writing this down?
I am.
Okay. Why don't you have your booklet here? Write it in your booklet. You're scaring me. What actually happened is your good old electron didn't... Since 1897, we knew that electrons existed. Before then, your scientists actually had conventional current, which is the flow of positive charge. So if you have an electron traveling to the right, which is the flow of negative, then your positive charge is in the opposite convention. I cannot talk and write at the same time. Then your conventional current flows the opposite direction. So when all of these rules about circuits and resistance and current and voltage were being established, they didn't realize electrons existed. They literally thought that positive charge was flowing through a circuit. So they actually thought that the positive charge was being repelled by the positive terminal and being attracted to the negative terminal. And when J.J. Thomson in 1897 said, hang on guys, I've figured something out. It's actually the wrong way. It's the electrons are travelling from negative to positive. And then they went, oh no, oh crap, it doesn't matter. Because if you move 5 coulombs of electrons to the right, it's exactly the same as moving 5 coulombs of protons to the left. All right, so moving a charge one way with a positive is the same as moving it the other way with a negative. So it didn't really matter. It's important in the Year 12 ATAR course, okay? But here is our battery. Let's realise that if we took some copper and allowed our electrons to flow through this copper, then...
Very hot.
Yes. But we've got our positive and our negative, and you can appreciate that your electrons will go from one side of the terminal to the other, okay? So it turns out inside our battery, and I think I did this when I was young, I tried to peel apart a battery to figure out what was going on. It gets really messy. It turns out that you have a, cathode. Now I can never remember. You have one material that really wants to gain electrons in the middle, and you have that insulated by some insulating material because we don't want the electrons to flow inside the battery, so we keep them separated. And then the outside material just really wants to lose electrons, and that's your anode, I think. But they can't get there because there's that barrier. That grey is the barrier, and inside here they really want to lose electrons. So you're talking about something with a really, really positive electronegativity and something with a really, really negative electronegativity. And if you allow them to move from one to the other, that's how you get the electrons to travel. Now, It's insulated, yes. So the only way that your electrons can get from that terminal to that terminal is to provide them a pathway. Okay? In air, they can't do it because air is an insulator. Every centimetre of air needs 10,000 volts of electrical potential. So our little 1.5 volt battery, our electrons can't just fly through and around. It's just not possible. So they will just stay there as a reservoir of stored energy. Like water in a dam, if you keep the pipe closed, the energy stays there. If you open up the pipe, you can allow the water to flow from high gravitational potential to low gravitational potential. So that's the analogy I'm going to use when we talk about energy. We haven't looked at energy yet. Yes?
So how do you charge rechargeable batteries then?
I don't know.
And also...
Ask the chemist, teacher.
Okay. Are you sure the electrons are being repelled by the negative terminal? Or are electrons being stolen?
They don't want to be there.
Or electrons being stolen by the cathode?
Well, both. They're being pushed and pulled. They're being pushed and pulled at the same time, and we measure that as a voltage. So the higher the voltage, the bigger the push-pull. So you're looking at both effects. So they're being repelled. Imagine you have an excess of electrons here and an absence of electrons there. So if you have all of these electrons in a given space, they don't want to exist near each other. They're trying to repel. They don't want to be there. They're like a tightly compressed spring. And if you allow them to, you'll convert that elastic potential into movement.
So would they be ions?
For the time being, I imagine so. The substance that's in there, I don't know what the paste is inside there. Ask your chemist. Yes?
And then how does it work with like a battery just running out?
Yeah.
It doesn't.
Well, eventually, yeah. So your standard batteries, eventually, once enough electrons have migrated around, the voltage drops. That's like the pressure in your dam. As the water drops down, eventually the water is going to drop down to some level where there's zero pressure. And if there's zero pressure, then there's going to be zero flow of water. Okay? Now, again, yes, you can recharge car batteries. You turn the voltage around, and that pushes the electrons back from the positive back to the negative. That would be like turning on a pump, and that would pump the water back into the top reservoir. Well, that requires energy, doesn't it? So you've got to put energy in to recharge your batteries, and the energy is now stored as electrical potential. The voltage would rise back up to its operating voltage. That would be like turning on the pump and pumping that water back up to our top water reservoir. All right, so I'll try and explain it with analogies. Let's now go to... What? He has his hand up all the time. I don't know if he's just stretching or... Do you have a question, Emil?
Is there another analogy that we could use?
No.
If we don't understand what
elastic potential. Pushing on us.
No, that's worse.
No, because I'm about to explain it using elastic potential. Now, could you please understand that electrons don't like existing near each other? If I said, consider two electrons that I just spawned into existence. Now, we used to do a topic in Year 11 and they moved it to the Year 12 syllabus. But currently, we know that electrons would repel each other. There would be a force of repulsion. If I just spawn them into existence, then they would go flying off because they would repel each other. All right? But you don't need to worry about this because of purple not in syllabus.
my favorite apple.
So basically you liked it when it was in the syllabus.
Well, so you've got this, the force as a function of distance in meters.
Exponential.
It's inverse square, but I like your thinking. It goes down like the 1 on r squared, okay? So r initial, r final.
1 of x, right?
The equation is f as a function of d equals a constant, q1, q2, over r squared. And in fact, I'm going to put all of this in the purple not in syllabus just for your... But basically, the force drops as it gets further away. And in fact, the area under is going to be the work done. I wrote that the wrong way around. The area under that curve. Now, if it was just a nice rectangle, boom, it's length times width. If it's a curve or a mathematical function, you have to do calculus. You learn about anti-differentiation if you're doing method or spec this year or next. But you were all happy for me to go, consider two electrons are separated by a given distance. And you went, yeah, okay. What if I said, consider this mitre box at a height of 2 meters, and you go, yeah, sure, I've got it, I can see the box, I can visualize it, I can draw it, I can say h equals 2, m equals 5. What I've done is I've just given you an example of stored gravitational potential, right? There's energy stored in that because of its height above the ground. So too, there can be energy stored in a charge because of its position. If I wanted to force those electrons together, imagine we said, all right, they're here at the moment, the force of repulsion, and I've got my two hands like that. And then I bring my hands and I force them closer together. Let's say I get my hand. There's my hand. Looks the same. Been drawing hands the same for the past 28 years. And I bring that electron so that he's here. Okay, so I move him. Well, I would do work. All of this area underneath is the amount of work that I had to do to bring those two electrons together. Okay? And so there's stored energy, like a compressed spring. Imagine I had a spring and I went, and I did that. You go, okay, yes, there's a store of elastical potential. If I let it go, it goes flying off. Here is a box. I'm going to lift it into the air. It now has stored gravitational. So hopefully you can appreciate that if I try and force these two electrons together, they are now in a higher electrical potential. They have more energy stored because of their position near each other. Are you happy with that idea?
Yes.
If I let them go, shoom, they go flying off. How far would they go?
Depends on...
No, they're in a vacuum, there's no mass, they're infinite distance away. So they travel off with an infinite distance. They have a finite energy, right? A certain amount of energy was given to them, and you go, all right, you ready? They go flying off. They will travel off forever. They'll go to an infinite distance where the force of repulsion is zero. I'm forgetting where I'm going. They now have, because of their position, they now have zero electrical potential. Yeah? They've got no more energy due to their position next to each other. Okay? So, with that in mind, I'm now going to introduce the concept of energy that we can give charges. I can give mass energy by lifting it up a certain height. I can give springs energy by compressing them a certain distance. And I can give charges energy by pushing them to where they don't want to be. Okay? The mass doesn't want to be up there. The spring does not want to be compressed. And the electron does not want to be near any of the other electrons. Put your hand down. It's probably going to hurt your shoulder.
No. What is R in that graph, that equation?
D. It's normally R for distance. So sorry, yep, let's call it D initial.
S.
And D final for distance. Okay? So, we now have an equation that relates how much energy you can give a charge. All right? And this is known as the voltage. So, voltage, I'm just going to rearrange this equation. Voltage is work done per unit of charge. Okay? Work, remember, is the transfer of energy, or the difference. So, put that in a box and highlight that sucker. The key thing here is we need to refer to the difference. So sometimes we put a delta out the front of the V. When I talk about that box having 100 joules of energy, it's with respect to the ground. So it has a difference in energy from the ground, zero potential, to there, 100 joules of energy difference. If I take a spring that was uncompressed and I give it 50 joules, it now has 50 joules of elastic potential compared to its unstretched. I could go the other way and stretch it out the other way and have 50 joules negative potential, 50 joules. With this, we need to look at the difference in electrons from where they are to where they might be. Okay? So maybe it's an electron on one side of the battery compared to the electron on the other side. It's like comparing a kilogram of water in the top dam and a kilogram of water that's now flowed down to the bottom dam. Which one has the least gravitational potential energy? The bottom dam. Good. And we can measure the difference in energy if we know the height and we know gravity. Here, if we know the voltage, we can figure out the difference in energy on the charge. Another way to remember this, and I always found this confusing, just remember that 1 volt is a joule per coulomb of charge. Okay? And we'll just label, sorry, that don't mean to confuse you with my red purple pen. 1 volt is a joule of work that's done on a coulomb of charge. Okay? And we'll just label this equation here is called the electrical potential difference. Okay, sometimes called PD, potential difference. So you always have to compare the energy with respect to another point. And we don't often do that when in year 10 you just go, what's the energy of a box on a desk? And you go, well, there's the height. Well, okay, but remember, we're on the second floor, so we're actually 4 meters above the ground. So is the box 1 meter off the floor, or is it 5 meters? But then the floor,
That was my impression.
the floor is also 15 meters above sea level. So is this box now 1 meter, or is it 6 meters, or is it 22 meters? Where do you put your h equals 0?
Would it be in the centre of the earth?
No.
Why not?
We don't worry about going into the centre. You can stop. You're going to be making Cameron think about drilling. No, we just go with the sea level. Sorry?
9.8 measured at sea level.
Yeah, but it doesn't change much. It doesn't change much. From here to sea level, the gravity doesn't change much. Could we look at our gravitational potential energy analogy? Let's put it down. Obviously, this is what Mr. Murray was talking about. If I took a mass at h initial equals 0 and I lifted it up to a certain height, let's call it h final. So here it is up here. Okay? So there's your mass and there's your mass. Your h final is going to be called delta, difference in height. Because remember, your difference, your delta, is going to be h final minus h initial. Well, conveniently, if we set our initial equal to 0, then your change in height is simply the final height. Okay? We have an equation that says EP equals mgh. But really, I'd like you to know that it's actually delta EP. It's the difference in potential energy is mg delta H. Now we can use this equation for Sam Rose. You can say, well, the delta H of the box in the classroom was 1 meter. We don't care that the box is 22 meters above sea level. We're just looking at the difference in height from start to finish. And then you will get the difference in potential energy from the floor to the table. Okay? And yeah, the smart kid in year 10 goes, well, hang on, I could slide this ball along the floor and outside, and then I could kick it out off the balcony and it would fall a further 10 metres. Well, then your delta H would now, instead of being 1 metre, it would be 11. So, we could say that the energy, the difference in energy per unit mass could be written as GH. All right? This is sort of your energy per unit mass in a gravitational field. Energy per mass in grav field. Well, I've written that very similar to the energy per unit charge, which is another fundamental quantity in nature. We have a measure of V. And so this is your energy per unit charge in an electric field. Now we're getting really philosophical here. Electrons produce fields, and the fields travel out into space. And another electron can be interacting with that field. We call that an electrical repulsion. Now throw all of those electrons into a battery, you got a ton of electric field there. And the measure of the strength of that field is going to be measured in volts. So I could come back to my battery and measure the difference in electrical potential. So, the last thing we're going to do, and then I'll stop talking. Consider this battery again. We say that the electrons are going to jump out here, and I'm going to give them a lot of jiggle brackets. I had a book when I was young, and you might have been lucky enough to have this book. It was How to Draw Comics and How to Draw Cartoons. And the... What?
The jiggle lines.
Several times.
When?
Several
At least
times.
twice.
The neutrons?
No, like
When did I talk about jiggle lines? Oh, temperature.
Yeah.
Yes. Well, now we are talking about a high electrical potential. The analogy is a bit upside down. If it was water, I should turn my battery upside down. Oh, there I have there. Oh, okay. Because we're going at the bottom, we're starting with a high electrical potential. As they go through the wire, they lose energy. That's one of the things about circuits. We need to have a circuit. We've got to have some kind of resistance in here. Okay? So this might be a resistor. And then when they pass through that resistor, they have low electrical potential. And then they return back to the top. Okay? Now, we don't know what the actual energy of the charge is, but we know the difference on one side to the other. It's like saying, I don't know how high the floor is from sea level, but I know that the table is 1 metre from the floor. Okay? So again, a year 9 kid in physics doesn't have to go philosophical with the questions. Kid, just use MGH. Oh, but where is the classroom? Is it in Colorado, which is 6,000 feet above sea level, or are we in that plane in America, which is actually below sea level? Because then we have positive. No, don't worry about, zero. We're going to look at the difference.
Wait, so how can you be below sea level?
You can. There's a place in America.
Both in Africa.
Africa. It's in a desert somewhere. There's a desert somewhere that's actually below sea level.
It's like a lifesaver. Like
This is
those
below sea level.
the lollies that like go,
It's like
they're like
crater.
I
like
do.
go in.
I do. Yeah, like lifesavers. All right. So here, remember all of our electrons. They're all jammed in there. And I want you to think, guys, boys, shush. Here are all of our electrons in that outer area, and they don't want to be there. They want to get to low potential. So when you see a battery and you go, oh yeah, there's a battery, you go, someone had to put the energy into that battery. Someone had to extract that paste and do work on that material so that it had a difference, it had stored electrical. All right? So all those electrons that got jammed into there and they don't want to be near each other, and if they're given the chance, they will race around through a circuit. They have to lose their energy. Okay? So it's a bit strange, but potential difference from one side to the other. Each coulomb of charge that flows, in this example, let's say we have a 1.5 volt battery. All right, so here's your 1.5 volt battery. You get your voltmeter and you measure the electrical potential across the battery. It says 1.5 V. That means that each coulomb of charge transfers 1 joule of energy. But one electron, Q equals 1.60, is going to do work equals QV. We're just going to rearrange the equation. Voltage is work per unit charge. And we would say 1.60 times 10 to the negative 19 times 1.5. It's not much, 2.40. Hold on. Put your hand down. Have you written this down? You haven't. It's empty. It's blank. You've written nothing.
I already stopped now. They just... Anyway, now that you stopped, sir. Why do batteries lose charge over time then?
You already asked that.
If you leave them,
Yeah.
they shouldn't.
They do.
Well, there might be a little bit of corrosion. The paste, if I don't know.
Because like,
Ask your electrician. Ask your electrician. Remember, lots of electrons. So for a battery to do a significant amount of work, in joules, you're going to need a lot of electrons because each electron on their own is only giving a tiny amount of energy. So if we want to be transferring, a joule of energy, we're going to need, 10 to the 19 electrons. But remember, we can do that. There are lots of electrons. There's plenty of them available, and we can have them flow through our resistor with a certain current, okay? Next lesson we're going to combine all of these equations. But you're probably wondering, we could leave, if we left Q equal to E, then we could say that work equals EV. And we could say that that equals E times 1.5 volts. Or we could say 1.5 EV. This was our unit. Oh, not purple, red. We looked at the electron volt. And so now it might start to make more sense when I explained in nuclear physics that the electron volt is the energy that an electron gains as it accelerated over a potential difference of 1 volt. This electron did 1.5 EV of work. Chemical, not much. Remember, 1.5 EV is stuff all. A chemical battery does not have as much energy as an alpha emitter. Okay? So if an alpha particle goes flying out with 5 million, your piddly little electron can only provide 1.5. But anyway, we'll stop there because I'm getting a little tired.
5 million electrons.
5 billion electrons.